Okay, so let's start. Welcome everyone. Happy to see so many people here in the tutorial. This tutorial will be all about creating and analyzing multivariable Earth observation data cubes in R. And as I said in the plenary presentation, it will consist of 3 parts. So the first part we're going to cover this morning is basically an introduction to Earth observation data cubes, and mostly with examples on the gdalcubes R package. The second part, which we will cover in the afternoon, we'll cover some examples on how to use data cubes to combine imagery from different Earth observation missions. And then we'll also have time for discussion, summary, and some practical exercise. So originally, actually, I was preparing to do this as a 2-hour tutorial and then repeat in the afternoon. So that was some spontaneous change we did. But that I had quite some material time, but we also have them. So at any point, if you have questions or call anything else, so feel free to interrupt me or ask or raise your hands or anything. And also in the end, we will have enough time to do practical exercises for you. My document here is a markdown document. This is rendered through HTML. And the most part of the first part, I'm going to do live in our studio, which sometimes will need us to wait a minute or so until the processing finishes. But let's see how this works. Okay, speaking about the R Markdown stuff, so there's a GitHub web page where you can find all the materials. So this is my GitHub account, and then OpenGeoHub Summer School 2020. And there you can actually find 3 separate Markdown documents, R Markdown, tutorial 1, tutorial 2, tutorial 3. And a short summary and some installation instructions if you want to do the practical exercises as well. So you have to install the packages, and also you have to download a file, which is a smaller version of the dataset I'm going to process live here. So that's the Landsat 8 dataset I was just talking about in the plenary. And I actually hope the download link works, because it does good. Because yesterday, so the university which is hosting this just announced that they're going to do some updates this morning. So, but apparently it works. So that's good news. Okay, so let's go to the rendered HTML output of the Markdown document and go on. So as I said, we will use a Landsat 8 dataset. So we have 180 images. That is surface reflectance images, so that means they have been atmospherically corrected. And I've downloaded this from the USGS portal called ESPA, so which is very convenient, because then there you get the surface reflectance data already. And these data cover a small part of the Brazilian Amazon forest. And as I said, I will use the full resolution data from my computer, so it's actually a small external solid state disk drive here connected to my computer. But feel free to use a smaller data set as well. But anyways, the original 200 gigabyte data set is also available online, so there's a link here, and then you can download it as well if you want to try at home. So I don't recommend to use it now, but probably it will crash the Wi-Fi, but I don't know. So please use a small data set now. Okay, so then what you download is a zip file, and that contains the images, and then please make sure to unzip it. So I have some R code for this. So this is the R command to download the file, and then the command to unzip it to the directory in the current workspace, L8 Amazon. Okay, so some motivation for the package again. So I've shown this figure in the plenary already. So the point we start with is that the raw satellite imagery we want to analyze is mostly distributed as a collection of files. And that can be on download portals of the space agencies or data providers, but it could also be in cloud environments. So if you're doing something on Amazon Web Services or Google Cloud, they already, for example, have all the Landsat and Sentinel-2 data, but it's still only the individual images as a list. So, and then you need to do something more to create, for example, to do time series analysis or so. So that's actually the similar problem. So you just get a list of files or images, and then you need to do something more. And that's what my package actually helps you a bit. So yeah, as I said, the problems we typically arise are that spectral bands have different spatial resolution in Landsat and Sentinel-8. We have images that spatially overlap. So if you have images from different swaths of the satellite, or also from the same swath, but next images where it's actually cut, then these parts overlap. And also the time series, if you have larger areas, are pretty much irregular. So for Landsat, the revisit time at one location, it's 16 days. So that's pretty much regular if you just have one point. But if you have like an area which covers more than one tile from more than one swath, from the adjacent swath, the image could be like collected a few days later or so. So then it's not regular every 16 days, but maybe every 16 days at one region, but maybe always like 3 days later at an adjacent region. So that makes this thing a little bit more complicated. And yeah, that's what the package actually helps you with. Okay, so I've shown this figure already. So this is one 4-dimensional data cube. So you have latitude, longitude, could be X and Y in the projected coordinate reference system as well. You have bands or variables and time as dimensions. And that's the data model of the gdalcubes library. So everything you do is 4-dimensional. Of course, you can then reduce dimensions and then have one dimension with only one value or so, but it's still always 4-dimensional. So and then compared to the stars package, for instance, that's one of the limitations, but what I think actually a lot of use cases use these 4 dimensions. And it's possible, which we will see later, that to convert a gdalcubes data cube to a stars data cube and then do the processing further and integrate maybe some other data that have less or more dimensions. So yeah, just to be precise, so this is actually not really a cube because it has, as I said, 4 dimensions, and also the sizes of the dimensions is not equal. So you would probably call it hypercuboid if you want to be precise mathematically. But I think it's pretty much clear what we have data cube here in this context. And this is this 4-dimensional thing here. Okay, so as I've shown in the plenary presentation, to convert these collections of images you get to a data cube, it involves a lot of steps. And the good news is that there are already quite a few tools that can help you with that. So most importantly, there's GDAL, the geographic or the geospatial data abstraction library, which helps you with reading and writing all the different raster data formats that are available. So you don't need to care about data formats actually, because there's GDAL. And also what it automatically can do is convert images to different coordinate reference systems, do the resampling and cropping as well. So there's one utility called gdal warp, which essentially does everything in one step. And that is pretty useful. So the downside of gdal is actually that there is no understanding of time, although it has now a multi-dimensional API, but that still doesn't work automatically for image collections. But it works for something like climate net CDF files, which are multidimensional by nature. So these kind of things. From an R perspective, there is the rgdal package, which interfaces GDAL, and then you can pretty much do everything which GDAL does from R. That's pretty convenient. And then there's, of course, the raster package, which probably many of you use in your daily work, I guess. That is well established, very stable and reliable because it's out there for such a long time and so widely used. Downside of the raster package is that it's 3-dimensional only. So you need to do some hacking to get something like multi-spectral, multi-temporal data cubes into the raster package. So what you typically do, you have a raster stack where the stack dimension can be either time or bands. And then what you could do, for instance, is in R, use a list of raster stacks with the same dimensions to do something like multi-temporal, multi-spectral data modeling. Yeah, another thing is if you have really these irregular image collections, you would still need to write a lot of R code on your own to do the reprojection, rescaling, and temporal aggregation on your own. So that would also need a lot of scripting from your side. And then there's good news. There's a new version of the raster package called Terra, which essentially, in my understanding, I haven't used it much, but in my understanding, it's mostly a re-implementation of the raster package, which is with the same functionality, but with much better performance because a lot of functions are implemented in C++ now. So that's good news to have this on cran as well since this year, I think. And then there's a stars package, which I think is much more flexible in general because it has doesn't have any restrictions on the dimensionality of the data and also has these kind of vector data cubes. So if you attended the session by Appel yesterday, you know what I'm talking about. So it's pretty flexible. And what is also nice is that it has this lazy evaluation approach. So if you call plot, it only computes really pixels you see in the end. So that's also what's similar to Google Earth Engine, which automatically sees, oh, you're looking at a map of the world. So, and then automatically finds out, I don't need to process the data at 10-meter resolution because you have only, I don't know, 1000 by 700 pixels or so on your screen. So that's pretty cool and makes things a lot faster and more convenient. But stars also assumes raster data cubes that they're actually already data cubes. So the last example in the session yesterday was pretty interesting, where Appel tried to do to build a 4-dimensional raster cube from the Landsat data we will use today. And there, I think you saw that this involves a couple of steps and is still challenging and not so hard to understand and to read because you need to set dimensions manually and all the metadata. Okay, so then let's start with the gdalcubes R package. This is pretty new actually still, so it's on cran for a year now, I think, or a little more. So, and as I said, it uses gdal to read, write, and warp images. So we don't need to care about data formats. And the nice thing is also gdal automatically can read not only files on your disk, but in principle also files that are located on a web server or files that are compressed in a zip archive or files that are somewhere in the clouds, like Google Cloud Storage or Amazon Web Services. So that's possible with gdal. They have these virtual file systems, which are pretty nice. So this gives a lot of opportunities and a lot of flexibility to work with. And also, if you use the gdal warp utility, you don't need to care so much about the reprojection and rescaling because it does everything in a pretty good way and is also pretty fast. So to install the gdalcubes R package, you just have to run install packages and the name gdalcubes. So that installs it from cran. To install it from GitHub, it's actually a bit more work because it's, well, it's mostly C++ and then it links to system libraries and also it has a Git submodule linking to another Git repository, which is not so straightforward, but still doable. So I recommend using it from cran now because it is pretty easy. And if you use Windows, it has all the gdal proj and all the other libraries directly in the library file you get on your computer if you download it from cran. But that's also the reason why the package is actually pretty big. So on cran, you frequently get some warnings that your package is like 80 megabytes in size or so, but don't care so much about that. Okay, so once we install the package, we can load it with a library command, library gdalcubes, and then, for example, tell that all the computations in the following may use up to 8 threads. And this is the gdalcubes options function that takes 1 argument thread. So I'm going to cover this function in the end of this first part again and tell you what other options there are. And please make sure that you have version 0.3.0, which is the latest on cran. Okay, so now I'm going to switch to my RStudio session because I want to do the commands actually live on my computer. So let's see. So this is my RStudio session, and this is the exact it's actually the same document, but the R Markdown. So is it large enough? Can you read it at the back? Good. All right, so I'm just scrolling through the document and then don't need to install the package, but I need to load the package and then tell the package I want to use up to 8 threads in the following computations. So that doesn't mean that I always use 8 threads, but it can use up to. So that depends a bit on how the data cube in the end looked like. Okay, so we check the package version and it's, as you see, 030. Okay, so the first concept you need to understand when you want to work with the package is the concept of image collections. So what we need to tell gdalcubes first is where our satellite data images come from and how they are organized. And in this case, it's just on my external drive. I can show you here in the file browser. So I have one folder here. L8 Amazon full, and then you actually see that these are 180 folders, which something like 2,000 items. And if you check out one folder, which is essentially one image, you see that there are, for each spectral band of the data, there's one geotiff. Good. So that's the organization of our data, and let's go on with the R script. At first, we just find these files in R, and this is a list files functions which takes the directory and the pattern, so that I only have to find the geotiff files. I'm doing it recursively, so that scans all the subfolders as well. And I'm saying that I want to get full names, which means that they contain the full path. So if I run it, it just provides a list of files you have, and that's, well, the path to the individual images, and nothing more. So I can print it and check how many there are, and these are 1,800 because we have 10 spectral bands, or 10 bands actually. 3 of them are actually metadata from atmospheric correction, and 7 spectral bands. And so that means 180 images, so 1,800 files. And now if we want to compute the file sizes in gigabytes, for instance, we can check and sum the file sizes of all these files. And so that's evaluates to 271 gigabytes, which, yeah, is already challenging because it, of course, doesn't fit into my main memory of this computer. Okay, so we have seen that every image is actually represented in a directory with individual files for spectral bands. And now what we want to do is we want to work with all the images as one single object. So, and if you use Google Earth Engine before, you have the concept of image collections. So that means you just import an image collection and then do something with it. So, and this collection contains of all images. And it doesn't mean, or it doesn't matter which spatial reference system they have, where they are located, and so on. So they're simply thrown into one thing or one object that can be used for analysis. And that's pretty useful. And that's what we also do with the gdalcubes R package. And we also call that image collection. So what we typically do in gdalcubes is that we need to iterate through all the files we are interested in once and extract a few metadata. So for instance, for each file, it's derived when was it, what is the recording date of the image, to which spectral band it belongs, and what's the spatial extent, what's the spatial reference system. So, and that opens every file once, extracts a few metadata, but it doesn't read any image data. So if you're familiar with GDAL, with the library, it calls GDAL open, but doesn't read any image data essentially. So yeah, and then actually we store the metadata we have just extracted for each image in a file. And that's a single file database called an SQLite database essentially that has all the metadata, and that's what we call an image collection. So we can run it with a create image collection function. I've just run it. So and that takes a while because it opens all the file once and extracts it later and stores the result as a l8.db file in my current workspace. And we typically only do this once because then later on, we're simply just building data cubes from that interactively. So the advantage of this is that if we create a data cube later on, which only covers a small subset of the spatial area of the original data, we can immediately find out which images we do not need to read at all. So it makes things a little bit more efficient. So it's essentially like an index for our images we have. So there's one magic parameter here, which is the format parameter. And there you give a string L8SR, Landsat 8 surface reflectance. And that's actually like a recipe how to read, how to extract the metadata. So some metadata like the spatial extent and spatial reference system can be easily extracted with GDAL. But as I said, GDAL doesn't know anything about time. So there's no standard way to extract the observation time or recording time from the data. And this is like a recipe which knows how to do that, for instance, in this case, for Landsat 8 surface reflectance data. And that's what I call collection formats. So that's one thing what gdalcubes adds on top of GDAL. So it adds these collection formats and knows how to understand these image collection formats or the files that are on disk. And it also knows about the spectral bands. So GDAL, if you have one file like band 4 of the Landsat 8 data set, GDAL doesn't know that there are other bands which belong to the same image. And this is also what this format argument does. I'll cover that in a minute. Right, so as I said, the image collection is essentially just an index to our data. Typically, it consumes something like a few kilobytes per image, so it's not something which contains any image data, so it's fair. So in our example, it's 0.5 MB or so, not something you really need to worry about. Yeah, and you typically do it only once, but there's also a function to add images later on. So if you download more recent images, then you can add them later on without scanning all the previous files again. Okay, so if you created an image collection, there's also a function to read it from the file. So without scanning all the files once, which is just the image collection function, and then we can print the object in R. And that gives us a few metadata. So this is essentially the image. I get the first 6 images. They have a name. They have a spatial extent. They have a recording date time. And they also have the spatial reference systems and information about the spectral bands we have. And some metadata on them. Yeah.
The image are not yet in the RAM.
No, nothing.
Just hyperlink.
Yeah, kind of. Yeah. Well, they're actually not open. So they were opened once there. Exactly. So right. So that gives us some metadata on the image collection. And so yeah, as I said, the format argument does kind of magic because it understands how the product is actually organized. And this is actually also pretty difficult for us if we start working with a new data set, for example. So this is pretty much, there's no standard way how the space agencies organize their data. So for instance, if you have MODIS data, all the bands are in one HDF4 file. If you have Sentinel data, you have a complete, well, you have a directory structure where at some point there are JPEG 2000 files for each band. And for Landsat, it's geotiffs. And also they have different file names where the date time of the recording is encoded. And that stuff is a bit, yeah, you have to find out and then try to derive a collection format out of this. So yeah, about collection formats, so these recipes how to create and extract all the metadata. There's a function collection format, and that lists all available collection formats. So the collection formats that come with gdalcubes, it's not so many these days. So let's go through it. So it has 2 chirps precipitation dataset formats, some ESA climate change initiative soil moisture data formats, which we'll use in the second part today. Then we have global precipitation measurement mission data, but only for very specific products. So I mean, all these missions have a lot of different products they deliver, and probably this format will not work for all of them. Then we have some of Landsat 8. We have a few MODIS collection formats. one also for PlanetScope data. And well, Sentinel-1 is actually, it's not provided, it's only on my development version. So that was just to try to get Sentinel-1 also into it. But that's a bit more difficult because the files you get from ESA, they are not auto-rectified. So that means they have the ground control points. And until now, so the assumption of gdalcubes is that the imagery is already auto-rectified. So what you would need to do is to do something like applying the Sentinel toolbox on the data to rectify it, and then you could work with the data properly. Anyway, for Sentinel-2, level 1C and level 2A data, there's a format. And also for Sentinel-2 level 1C data on Amazon Web Services. And on I think that's a French cloud portal, Theia. Yeah.
Landsat 7 and 5 is not available.
Actually not, but it's not so difficult to add. It's not difficult to add, so yeah. Speaking of them, they are actually just JSON files. So JSON is JavaScript object notion, I guess. And in that JSON file, you see a couple of regular expressions, how to extract the relevant data format. So, and if you have an example, you can relatively easy, I mean, regular expressions are always a bit, well, easy. It's quite easy to add something wrong in regular expressions, but you have a couple of examples. So all these collection formats are essentially in a GitHub repository, and let's see the Landsat 8 format. So it describes the spectral bands it has, some metadata, and essentially a list of regular expressions, how to extract the datetime, and how to find out whether images belong together to the same images, but have different spectral bands. So in principle, that is extensible. It's also documented. I hope I find the link. Yeah. It's documented. So it's definitely possible to add something there. And if that doesn't work, just add a GitHub issue, and then it's probably gonna work out fine. Okay, so then we have an image collection, and we can derive the spatial temporal extent with the extent function and specify that our result, well, coordinates should be latitude, longitude. And then we get a list, left, right, top, bottom, starting date or the earliest date of the earliest image and the latest. So it covers quite a few years, but once I downloaded the data, so that was filtered by cloud coverage. So it's not like it's the complete Landsat 8 imagery for this region of interest. So there were some filter during the download. Okay, so this specification of coordinate reference system is probably most useful. So you have just a string with EPSG, a colon, and the number. But in principle, that can be anything that GDAL understands. So it could be a WKT string, it could be a Proj4 string, or yeah, any other format that GDAL understands, which is also pretty good documented. Okay, so now we have an image collection of our data. So that means we know where the data comes from. The next step is that we need to think about our data cube. So how shall it look like? So, and that's what we call a data cube view. So that defines the geometry of our target data cube. And that includes the spatial temporal extent, the spatial reference system, the spatial size and the temporal duration of the cells in the cube, and also two arguments on the creation of data cubes, which is the spatial resampling we use and the temporal aggregation. So the example again, if I have a data cube where one cell actually represents 1 month, the temporal aggregation defines how how values within that month, if you have several values, several observations, are combined for every pixel. So that's the temporal aggregation. The spatial resampling is what is done before when you call GDAL warp. So when the images are reprojected, rescaled, or cropped. And there are quite a few methods available. So for the Spatial resampling actually can do anything what GDAL does. So that includes nearest neighbor, maximum, minimum, average, median, bilinear, bicubic, some splines, I don't know, quantiles probably as well. So there are quite a few options. For the temporal aggregation, there are minimum, maximum, sum, mean, median. I think that's it. So, yeah. Okay, so the data cube view is just like the geometry of our target data cube. And to create this, we have the cube view function. And that takes the argument spatial reference system. Again, in this case, we just use Web Mercator because, well, maybe we're just interested in visualizing and to try out things. So that may not be the best choice for your analysis, of course. But anyway, we use it here. And we say the extent of the target data cube should come from the image collections. And that's like a shortcut to define that the extent should come from the image collection, so it contains the full extent of the collection. And then we specify the size of the pixels in space, which is 500 meters for now. So we just want to get something like an overview data cube and say that the temporal resolution should be 1 year. So this is like a bit simplified ISO time duration format, which takes a P for period and then an integer number in the unit. So that could be month, days, hours as well. And then we're defining the resampling and the aggregation algorithm. And then we can execute it and print it. And then it tells us the dimensionality of the data. So we have for each dimensions, T, Y, and X, we have low and high values, the number of values, and the size of individual pixels. So in the same way, we could create a 100-meter resolution data cube, but this time we explicitly specify the spatial extent as a list with arguments left, right, bottom, top, T0 and T1. So that's a small sub area of our original area with a bit higher spatial resolution, 100 meter. And then we can also again print it and then see that in this example we have 1000 times 1000 spatial pixels and 5 points at time, 5 years actually.
So the same question as before. At this point, is in the memory, the image or not?
No, nothing. So
they are in the hard disk.
They are on the hard disk, yeah, exactly. Yeah. As they are downloaded actually, so nothing changes there. Right, so this whole data cube view concept is independent from actual image collections or any data because it just defines the geometry of our target data cube. So if you look closer to it, you don't see any spectral bands because it abstracts from the individual data sets in order to be able to reuse the same cube geometry to different data sets. We come to data cubes then in a minute or so, which is essentially the combination of a data cube view, so the geometry of a data cube and the image collection. So the third option to actually specify a data cube view is to provide an already existing view. So in this case, we use our sub area at 100 meters spatial resolution, and then we just override some of the parameters. So we don't need to specify it completely, but say that maybe only the starting and end date are changing and our temporal resolution. So for instance, we're creating a data cube or the data cube view with for 1 year of 2015 at daily temporal resolution and 30 meter spatial resolution, which is what Landsat is all about. So then sometimes you get these warnings. And this is actually not really bad. It's just that it informs you that the extent is actually, you can't divide, or the extent is actually not, if you divide the extent by the cell size, it's not an integer number. So you would end up with half a pixel or part of the pixel at the right or at the left or top or bottom. And in this case, the extent is just slightly extended to both sides where it actually extends. So in the X direction, in this case, we enlarge 10 meters at both sides and the same in the Y direction. So that means just that you have complete pixels also at the boundary of the cube. Right, so that's what I said. So the data cube actually doesn't contain any information in spectral bands because it is independent from particular data products. So then the more exciting thing is to create data cubes now. So we have defined the image collection, we have defined the data cube view, so the geometry of our target data cube, and then data cube or raster data cube is just a combination of the two. And we have the raster cube function that takes both of them as arguments, essentially. So what we can do is we can create a data cube here with the raster cube function and assign it to a variable L8 cube overview, which takes the Landsat image collection and our overview data cube geometry. And we can print it again. And that is actually similar to the image collections that the data cube view. So we see the dimensionality again, and we also see the bands. So it's really the combination of image collections and our target data cube geometry. So, but still, so this is a data cube, but it's not yet reading any image data from disk. So this is similar to what stars calls a proxy object. So it's just like a pointer. So it knows where the data is and what to do with the data, but it doesn't do it. So it tries to delay everything until you call plot, for example. So because then you see pixels on the screen, so that means you need to read the data. So that's one of the concept of the package, which actually applies to almost everything. And we'll see later, so also for complex workflows. So in the same way, we could create a data cube called L8 cube sub area, and yeah, just use the same image collection, but our sub area data cube view, and then print again the dimensionality, well, which is essentially the same. So the dimensions from the data cube view and the bands from the image collection. And we could also create a daily data cube for the year of 2015. And then you again get the dimensionality, number of pixels, and the spectral bands. So yeah, this is all very cheap until now. It's just returning proxy objects, but not reading any image data. So as I said, so the package tries to delay all the computational intensive parts as much as possible. But yeah, the returned object knows about the bands and of the data product. And yeah, most of the time we don't need to read all the bands probably. And there's one function, select bands, which can only select a subset of the bands. So in the example here, I'm just selecting the RGB bands, which are bands 2, band 3, and band 4. And the select bands function takes the input data cube as first argument and the names of bands as a vector as a second argument. So there's also one nice thing with the package is that you can work with band names instead of just integer indexes. So, but yeah, you still would need to look up in the Landsat 8 handbook which band is actually red, green, and blue. But once you know that, it's a bit more convenient, I think, to write strings here. In principle, that would also be possible if we change our collection format to rename this to red near to red, blue, whatever. Okay, so let's execute this and then print this object. It's actually the same. So it's again only a proxy object, but the result has less bands. So it only contains bands 2, 3, and 4, and has the same dimensionality, of course, because we just derived a subset of the spectral bands. And this is essentially a data cube, but still not reading any data. So there are some utility functions on data cubes. For instance, you can extract the names of the bands with the names function, which then gives you a character vector with the names. You can extract the spatial reference system of the data cube, which gives you a string. You can get more metadata on the bands or variables of a data cube, and that gives you some metadata. And there's also the dim function to find out the dimensionality of a cube, so how many pixels or cells there are actually. Okay, let's get to the part where data is actually read from disk, and this is where we plot the data cubes. So the plot function, of course, if you know R, you know the plot function, so that can be used to visualize data cubes. And yeah, calling plot will then start reading and processing the data. So for a simple RGB plot, the plot function takes an RGB argument, and where you have to specify which of the bands are the red, green, and blue channels. And in this case, it's band 4 is the red, band 3 is the green, and band 2 is a blue channel. So we have to kind of reverse the order of our bands in the plot function. And that's what we do here. And then there's an argument zlim, which essentially defines the black and white points of the images, of these color channels, so to say. So that means 0 is actually completely dark per channel, and 1500 is, well, white per channel. So let's run this and see what happens. So yeah, you get a progress bar because now it's really computing things. And that takes a while. So it takes like a minute or so, I don't know. Because now it reads, it actually has to open all the files because our extent is just the complete area. So it's just the overview data cube view we have just created. And so it needs to open all the files and then, of course, only work on, I think, 300 meter resolution. But still, it needs to open files and do some resampling and aggregation per time. So, for instance, if we have several images per year, so it also does something like a median aggregation of values per year in the time series, and then to get something meaningful. So yeah, as I said, it takes the duration, and it takes some time, and also it's yeah, it's a bit of work for the computer here. But anyway, let's wait until it finishes and then see how the result looks like.
And of course, as with plotting, you can also create an object and having the summarize pretty much inside the
Not really direct. So yes, so there's a function, for instance, to create a stars object, and then you have a stars object and can process further. Yeah. And also you can convert it to raster, but actually that always writes intermediate files to a temporary folder. But yeah. So that's how it looks like. I can try to make it a bit larger. So yeah, the plot function itself is also a bit slow sometimes because it's not so clever as the stars function. So I think the dimensions in space are like 1000 and a bit pixels in X direction and similar in the Y direction. So, and all the subplots actually have really this amount of pixels. So although we only see very few of them probably. So this is our initial data cube where we have like a very regular structure and we can readily use to analyze the data further. So what we see here is that clearly that we have these typical organization of Landsat images where you have, I think you can see it here quite well, overlapping areas, and also these images here come from a different map projection than here and all that stuff. And now it's everything in one data cube, which is pretty easy to process, as I said. Right, so we can also create a data cube from our sub-area data cube or plot the data cube. So here we just also select the RGB bands and apply the same plot parameters. And so that will again read the data and then do everything. And then in the end, it will plot it. So it's a bit faster. We have a bit smaller area now. So that means it will not open all the files, but only the files that intersect with our region of interest. Good, so approaching 100%. So let's see what happens. So yeah, it's just one sub area at 100 meter pixel size. Yeah, and then if you have good eyes, you maybe could see some areas where the forest has, or some forest loss is actually occurring. Okay, so that was the RGB plot, but we could also plot bands individually. So we can do something like having a two-dimensional plot layout of bands in time. So what we do in the next example, I'm just start to process it. Although it actually will not process it because it already did it. So in the next example, we just again specifying these limit parameter to kind of adjust contrast and brightness. We have this key.pos argument, which adds a legend to our plot, because now we have individual bands, so we can really assign colors to values. And in this case, we use a Viridis color scale, which is a pretty good default choice, I think. So yeah, what we now get, and it's progressing slowly, is that you have like a 3-column layout. So this is the band 2. Then there will be band 3 and band 4 as individual columns in this plot layout, and individual rows mean the year, essentially. So yeah, and I also get a warning that this device is actually too small to plot all that stuff. So it plots only 5 years and not the full 7 years, I think. Yeah, that's what the plot function does. It's not super fancy what you can plot there, but I'll show you later how to also export your data cubes to other file formats, and then you could also do stuff in QGIS if you want to create a map or so. Okay, one nice thing is that if you process or plot the same data cube, but simply change these visualization parameters, is that it is not doing the heavy processing again. So it kind of remembers that you already processed the data cube and then uses it again and only assigns, well, a different color scale or so. So and that happened actually here because I have already evaluated this data cubes in the previous call to the plot function, but as an RGB plot, there were no progress bar. So the time it's actually doing something is only needed for the plot function itself. Okay, so the plot function does some further, or tries to do some clever things sometimes. So for instance, if you have a data cube that has only like 1 pixel in space, so it realizes, hey, this is a time series, so it will plot time series only. So that can be useful for time series plotting, especially we will see later that we have some functions to process data cubes to reduce dimensions and all that stuff, so that when you, for instance, apply a reducer function over spatial slices of the data cube and you end up with time series essentially, then this is pretty useful. Okay, so one problem we always have with these kind of data is clouds or other irregular values, cloud shadows, saturated pixels, whatever. And there's actually a possibility to apply a cloud masking during the construction of the data cubes. Because we do this temporal aggregation. So this is actually needed because otherwise cloudy pixels contribute to this temporal aggregation. And therefore there's a function called image mask. And what it takes is a name of the band and then values that are either acceptable or not acceptable. And then if a pixel in this band has a value that is acceptable, then it will leave the values of all other bands of that pixel the same. But if this is not acceptable, it will set all the pixel values of other bands to an A of that pixel before the temporal aggregation is applied. So that means it will not contribute to the data cube at all. But of course, we depend on cloud masks or other quality layers that they are provided with the data. And in this case, for the Landsat data, there's a band pixel QA. And I had to read the Landsat 8 handbook quite carefully to find out which values are actually okay. So I found out that there was a list of values I copied, and these values I listed here in this vector mean clear conditions. So I provide these values just copied from the Landsat handbook, and then I say invert the mask because these are the acceptable values. And then I say invert equals true. And then this doesn't do anything, just bringing everything into a list. But then the raster cube functions can take this list as an additional mask argument. And then these values are actually set to NA if there are no clear conditions. So we can do it. Again, create a new data cube, select the RGB bands and plot again, now with a mask. So it will process again for our sub area. And yeah, now with the mask, and I think the result will look quite a bit different. Although I also have to say that we applied a median aggregation in time, and that's already often quite a good filter for clouds because it's not, I mean, it's quite robust. So if you have a few cloud values per time series, it's kind of capable to filter out. Okay, so it's plotting again. And there you see actually that, I think in the previous plot, there were a few clouds here and then some clouds here. So that looks actually bad here, but on my screen, I see this is gray, which is the color for NA values. And that's exactly NA because in this year, we don't have any observation where there were no clouds. So that means this just stays NA and we don't have any information there. So yeah, but otherwise, other than that, I think the clouds are actually pretty good removed. And it's nice to work with. So yeah, I think actually these Landsat cloud masks are pretty useful by default. It's sometimes different for Sentinel data. Yes?
So this aggregation to the yearly time step, do I understand correctly? There's some averaging going on over?
It's, yeah, median in this case.
Median.
Yeah.
Okay.
So this is what I specify in the data cube view.
Okay, yeah, right, I remember. Okay.
Yeah. You could, in principle, specify a daily data cube. So if you just change the temporal resolution, and then you don't have that much aggregation.
Sure.
So only if you have images from the same swath that overlap at some area, there are sometimes more than one observation for the same pixel.
Basically very sparse cubes, like image of cubes if you have a lot of clouds.
Yes, yes.
So the images we see are not actual images, but within 1 year. So for 2014, you have, I don't know, 10 images, and then it takes the median pixel for within that year.
Yeah, exactly.
Can you specify like seasonality, or is this always like from the same? Can you repeat what P1Y was?
What do you mean with specifying seasonality?
So you don't average like, I don't know, a winter from a summer.
So that your result looks like only like month or so, January, February, and then median over all the Januaries from all the years.
Yeah, for example.
Yeah, we will see that later, yes. But that's not something which you can do directly at the beginning.
You have to make the image collection only with the Januaries.
Yeah, that would be
the Januaries, and then you have to.
Indeed, this would be an option, really. Yeah. Good idea. Yeah. Okay, let's go on. So I promised to show how to generate animations also, animated GIF images actually. So that's pretty easy. I mean, if you have a data cube, it's already, you can just extract plot time slices and then create an animated GIF. That's what the animate function does. It takes a data cube and then essentially the same arguments as the plot function does. If I call it, then it just uses the image magic library and R package to generate an animation, and it's, yeah, they're looking like this. And then I think becomes clear that there are some deforestation areas. So P 1 year actually means that it's like a value which is generated from a whole year. So it's not like only one point in time at one day or so, that it's like the median of 1 year. Yeah. Okay, sometimes, of course, we want to post-process or visualize our data cubes in other software or also maybe other R packages. And what we can do is export data cubes as netcdf files or as one netcdf file. So one data cube becomes one netcdf file, which is pretty straightforward because netcdf actually supports arbitrary dimensionality. So this is a pretty good and natural data format for data cubes. And the other option is to export data cubes as a collection of geotiff files. That means that you're not only getting one geotiff file, but for each time slice, you get one geotiff. And then with the spectral bands of the data. And both the netcdf and geotiff exports support compression and packing. So compression means that you can apply something like a deflate compression algorithm to make the data a little bit smaller. And packing means that by default, everything is double values, but you could convert it to smaller integer data values, which take maybe only 2 bytes by applying an offset and a scale to the values. And that's also why these sentinel data and all the Earth observation data come often only as integers, because they just want to save a little bit of disk space. So instead of taking 8 bytes per value for a double precision value, it just takes like 2 bytes. But then of course you lose precision in the data. But that's one option to save a bit of disk space. But that's just one detail which you can do. Okay, so let's look at the netcdf export. So I'm just creating the, using the overview data cube of the whole area and export it as a file in the current workspace. So that's actually not some easy to read function here, but every time I render this our markdown, I want to generate it a new file. So that kind of generates a random file name so that it doesn't overwrite any previous files. So yeah, this is pretty fast because again, I already plotted this data cube. So it realizes that, hey, it's already there. So I just copy it to that directory. So let's go to our workspace, which is here. And then I think, yeah, that's the file we just created. And this is a netcdf file, which in principle, you could also load in QGIS. Let's try that out. Yeah. Okay. And then you get a list of variables, which are netcdf variables, and that contains band 2, band 3, band 4, and some boundary variables that specify the lower and upper values of the pixel coordinates per dimension. So for time, X and Y. So we ignore this for now, but this is some standard. I think it comes from climate community on netcdf data. I'm not so sure, but that's what's often there in the images. So what you see then is actually a pretty strange looking image because it's essentially not like bands 2, bands 3 and 4 combined to an RGB plot, but it's only band 2 time 1 times 3, 2 times 3 as RGB bands. So that's not so nice when you visualize it in this way in QGIS. So what you would do typically is only, visualize one point in time, then maybe scale, I don't know, let's say, scale the color a bit. So, and then you see, this is the value of band 2 of the data cube at year 2050. Yeah, and then you could for example, change the date. But yeah, in this way, it would be a bit more difficult to create RGB plots, and therefore a geotiff export would be much easier, I think. Anyway, what you could do, for instance, is also to just click here and then extract some time series in QGIS, which I recently found out. And then you see how these values behave. So this is pretty cool. The only disadvantage here is that NA values are actually visualized as 0. So you have to be a bit careful here. Okay, just an example how you can read it in QGIS. Right, so there's a function to convert it as stars object, which is called STS stars. And yeah, that's pretty convenient. You just provide a data cube object to that function and it will convert it to the stars object. And then you can do whatever stars can do with it. And probably stars has also much more sophisticated plotting possibilities. So that would be pretty useful for plotting. And as I said, the write_tiff function can also be used to convert a data cube to a raster stack. But that's of course only possible for data cubes which have only one band or one point in time. Because as I said, the raster stack is only 3-dimensional, but we have in principle 4 dimensions. Anyway, so if we have we can call write_tiff, select bands and raster cube. So we create a raster cube of our sub area, but select only band 5. So we have only one spectral band. So that should fit into a raster stack. Let's try that out. Yeah, it will do the TIFF export, which if you don't provide any file name will generate a temporary file. And then X would be just a raster stack, which you could then plot. I didn't read I didn't load the raster package. I'll skip that for now, but it's a raster stack, so you can use raster function. I can probably use something like this. Yeah, then use raster functionality to plot these data cubes. Okay, one other example I want to show for visualization is that you can also use the map view package if you exported your data cube as a TIFF collection. So I know that Tim Appel, the developer of the map view package, will talk a bit about the package, I think on Thursday. So just here one example, you can use a map view package and then just use one, for instance, plot the first point in time of our raster stack, and then you get a nice looking interactive map. So yeah, it's quite an amount of pixels here, I think, for the package, but yeah. And then you can also change background layers and so on. Okay, good. So that's actually what I wanted to talk about on the creation of data cubes and plotting and all that stuff. So the next part is about the processing of data cubes. So you can not only create these data cubes and plot and export and animate, but you can also directly process the data cubes further. And there are some built-in operations to do that. And here's a table. Maybe I switch to the HTML view because the table does not look so nice in Markdown. Right. Oops. No. So that's the operations which are built into the package. So there's one operation, apply pixel, which just applies an arithmetic expression or more expressions on band values per pixel. So that's typically used to compute something like vegetation indexes or other indexes. So you get, from one pixel, you get all band values as input, and then you can do any arithmetic operations on it, and well, then use the result as a data cube. There's one function, fill time, which is a very simple method to do time series interpolation to get rid of NA values. But it can only do linear interpolation, nearest neighbor, or something like last observation carried forward. So you just repeat values until you get a new value. So that's pretty simple operations only, but sometimes useful for animations and so. Then there's a filter pixel function, which is similar to apply pixel, so that evaluates a logical expression on pixel band values. So that can be used to filter pixels which have like something like an NDVI less than, I don't know, 0.6. And then all other pixels are set to an A if they don't fulfill the expression. There's a filter geom function in the latest package version where you can just provide a polygon and then it will crop data cube values outside of the polygon, so they get set to an A. There's a join bands function which combines the values from some data cubes provided that they have the same geometry. So that's what we use in the second part of the tutorial in the afternoon quite a bit. Then there's a reduce space function which reduces the function over the slices of a data cube, over time slices. So that means the result is a time series only, but you can compute some summary statistics over like the spatial slices. And there's a reduce time functions, which similarly applies a reducer function over individual pixel time series. So the result is then only one image with summaries over the time series. We come to a few examples afterwards, so we'll go through the details of these functions as well. So then there's select bands function, which we already used to select a subset of the data cube band. And there's also window time function, which can be used to apply something like moving window reducers or moving kernels over time series of data cubes. So one thing I'm gonna use a lot in the following is the pipe operator in R. So that comes from originally comes from the Magritte package. So that's percentage greater than percentage. And actually that just means that the left-hand side of this operator is passed to the function of on the right-hand side as a first argument. So for instance, if you have like R norm 100, which generates 100 normally distributed random numbers, and then pipe this into the mean function, that means essentially that it computes the mean on this argument, so the mean of the random numbers. So I find that in my examples pretty useful. Sometimes it's just, so that's one of the concepts of the tidyverse, but I'll show you why I think this is useful, because it makes the processing of data cubes, if you have long process chains, pretty easy to read, I think. So one thing which you have to know about how this processing works internally is that it works chunk-wise. So chunks mean that it will only read something like subcubes or subparts of the data cube at once into the main memory and tries to process that. So even if you have like very large data cubes, it will not try to read everything into main memory at the same time. So that's one approach how we deal with external storage. Yes, so right, so I should mention that the sizes of chunks can be specified manually if you want to do some performance tuning, but I think the default is mostly useful. So, but of course, if you have a very specific application, you want to tune the performance, then you can adapt that. Okay, so let's start with the arithmetic expressions on pixel band values. So the apply pixel function, and look a bit more into the detail, what we can do with it. So as I said, it can be used to apply per pixel arithmetic expressions on band values of a data cube. And yeah, vegetation index are one of the most prominent examples. So it takes a data cube as first argument and then a string vector of arithmetic expressions. And then you could also specify the names of the output bands of the data cube, because the package alone does not know what you do in the arithmetic expression. So you need to define something like a name of the output if you want meaningful names. If you don't do this, you get something like band 1, band 2, band 3 or so. So what I do is switch to our studio again, and then load the Magritte R package to get the pipe operator in R. I'm also loading the color space package, which has pretty nice color scales and color palettes, with very good default values. And they also have like sequential scales as well as diverging scales and all that stuff. So in that case, I'm defining a color range as a function depending on the number of classes I have. And then I'm saying I want to use a sequential color scale called green-yellow. This is pretty well documented. So you can look that up. And I want actually lower NDVI values to be yellow and higher NDVI values to be green. So I have to reverse the vector which comes out of that function. So, and that function can be used and applied or provided to the plot function of the gdalcubes package. Okay, so now I'm creating a data cube which on the fly creates or computes the NDVI values. So what I do is create a raster cube as before. And we apply a mask. We use our sub area at 100 meters spatial resolution. We select the band 4 and band 5, so which are red and near infrared. And then we use the apply pixel function, provide a character arithmetic expression. So that is just near infrared minus red divided by near infrared plus red. That's the formula of the NDVI. And then I just tell gdalcubes that the result is called NDVI. And I also tell that I don't want to keep the original band. So the result only has the NDVI band. And here you see how I use the pipe operator. So I'm creating the raster data cube, pipe that into the select bands functions, and then afterwards apply pixel functions. And I think that's what the pipe operator makes quite easy to read. Okay, so let's run it. And as you realized, again, it's not doing anything computationally intensive. So it again returns only these kind of proxy objects. So it knows what to do and where the data comes from, but it doesn't do it until you call write netcdf, plot, or similar. So I can print it. It's a data cube object, proxy object, and it knows the geometry of the data cube and the name and some information on the output bands. And then, of course, if I call plot, all the processing begins, and it will on the fly create or calculate the NDVI. And then I'm using the color scale, which we just defined. So I specify a function as a color argument here. And I'm saying that the minimum value is minus 0.3 and the maximum value is 1 for the NDVI, and I'm plotting a legend. So 1 means actually that the legend is plotted at the bottom of the plot. 2, I think, means on the left, and 3 and 4, top and right. Oh, I think I forgot to load this package. So it couldn't find the sequential HCL function, so I'll try again. Yeah, there it is. So you see this nice looking color scale, I think, and then yeah, also where NDVI values are actually higher in the forest, of course, and then you see some other areas which are more yellow, of course. So yeah, as I said, so creating a chain of data cube operations still returns only proxy objects. So it knows what to do, it knows the size and the geometry of the data cube, but it will not start reading any data up to now. And then you call plot, and then everything starts. So yeah, in the example, we have just created or provided one arithmetic expression to compute the NDVI, but in principle, it's possible to mix that with the bands. So you can calculate several indices on the fly, and also, yeah, and then it's just, you need to provide a vector of expressions actually and a vector of names. So, but that works in a similar way. And also you can say, yeah, I don't know, you want to keep the bands and then you still have band 4 and band 5. And yeah, if you need them. Okay, similar to the apply pixel functions, as I said, you can use the filter pixel function to just set pixel values to an A in case they don't fulfill a logical expression. That's what the filter pixel function does. So the example here is a good example for how I use the pipe here. So it's just raster cube creation in the same way. Then I select the bands 4 and 5, then I compute the NDVI. And then I filter values which have NDVI less than 0.7. So it's a very simple example, but for example, I would probably get rid of most of the forest areas here. So they would be set to an A. And then I'll show another argument to the plot function, which is an A color. So the NA values are by default plotted using actually gray color, and I'm using some of the R called LS Blue now. So let's do the thing. So that of course does the computations because I call plot, and then we need to wait a bit, and in the end, yeah, let's see how it looks like. So yeah, so we got a lot of NA values now. So this is these bluish areas here. So, and because we fitted on the NDVI, we got rid of most of the forest areas here. Of course, that's pretty simple, but you could do more complicated expressions here as well. Okay, so some functions which are always useful are reduction over time and over space. So there are the reduce time and reduce space functions. Yeah, which you can do use to something like calculate median NDVI values over time, which we do in the following example. So reduce time. So let's start at the beginning. We create a raster cube again, compute the NDVI, and then call the reduce time function, which takes a vector of string arguments, and these string arguments are essentially a combination from a reducer function and then the band name. So in this case, we only have one. We only compute the median of the NDVI over pixel time series, but we could also add more expressions as a vector. So let's do this. So these reducer functions are actually built in the library. There are other possibilities besides median. It's minimum, mean, median, maximum, count, which just counts non-NA values. There's some variance in standard deviation, SD. And you might notice that we, in the apply pixel function and as well in the reduce time function, we are providing these arguments as strings or characters. And that's the reason for that is because these expressions actually translate to functions that are implemented in C++. So it's not any R code that is executed, but it's really built into the library. So it translates this into the median aggregation in the C++ code, which is implemented. So that's the reason. We will see later on how to do time reduction with user-defined R functions as well. Good, so this is the result. So yeah, actually this line here sometimes appears on my Linux computer. But if it's not actually not there. So it's just a plot device. If you plot it here, it's not there. So it looks good. There was a question.
Yes, does it for this type of calculations it takes the complete time series or the annual averages that we have to find out?
The annual averages. So these operations only work on the data cubes, not on the image collections. Okay, I have another example, which I'm not going to plot, but that shows you that in the reduced time function, you actually can specify several combinations of reducer functions and bands. So I have a band which I have a data cube with the NDVI bands, but also the red and the near infrared bands. So one nice thing about the pipe is actually that I can highlight this code and execute it, and it's returning the proxy object. So it's not executing the other things. So I can just execute these lines and then see how the result looks like. So in this case, this results a data cube with band 4, band 5, and the NDVI. And then afterwards, I apply 3 different reducers. One is median NDVI, one is a mean NDVI, and then the maximum of band 5 for whatever reason. So just a toy example, but I'm not going to plot it, but yeah, that would also be possible. I mean, I can plot it. Let's see how it looks like, and then let's wait for a minute. Yeah. So probably it will not look so nice. Oh, I forgot the pipe. because these resulting bands probably have very different values. So NDVI is scaled between -1 and 1, but band 5 is actually the original values from band 5, which are like between 0 and 10,000 or so. So probably plot will only look nice for either the band 5 or the NDVI values. So yeah, that being said, so it's not possible to apply different color scales to different bands of the data cube. So if you want this, you could, yeah, probably use stars to do better plotting. Yeah, exactly, as I said. So you see that the value range here is something like until 5,000 or so. And of course, you only see values out of range because the NDVI values are just too small. Yeah.
Second question. Why do you access, or I think I don't even understand the initial differentiation between this dot sub area of 100 meters and the L8 cube sub area? Like, what is the exact difference? Because in this case, I would have thought for the L8 cube, you access the bands, and with this one, you don't. I mean, both objects kind of don't access it. I don't get the differentiation.
Yeah, of course. No, so this thing here, so the data cube view, it's really just a geometry. And the idea is that, assuming you have sentinel data for the same region, you could reuse this object and then create a data cube that contains values from both Landsat and Sentinel. So that's the idea of these data cube view. The other thing is the raster cube, which then is the combination of both. And I think this proxy object is pretty useful because it doesn't let you write all the intermediate results in your processing chain. So if you really have a chain of operations, you don't need to, well, evaluate intermediate steps. And also there's potential to optimize the whole processing chain later on if you know the full processing graph, so to speak. Although I'm not doing that very extensively, so at some parts it does, but there are more clever ways to do that. Okay, so that was the result here. Let's do also the reduce space function, which reduces the data cube to a single time series, but applying summary statistics over individual time slices. So in this case, I'm computing the NDVI again and compute median NDVI and standard deviation of the NDVI as per time slice. And so yeah, it will again take a moment. So yeah, there are cases when the progress bar is actually not really accurate, but while I was implementing it, I learned that implementing good progress bars is actually not so easy. So what it actually does is it looks how many chunks the result data cube has, and then it just counting how many of the chunks are already evaluated. So if the result just has one smaller chunk of data, so you just immediately get from 0 to 100%. So, but if you want to process larger areas, it typically does something reasonable. So yeah, the result, as I said, is a time series with the median NDVI and the standard deviation. So of course, this is very few values, so it's only the few years here, but I think it just shows how this works as well. What is really useful often to get an understanding of the original data you have is this count reducer, and then doing a very high temporal resolution. So for instance, what I do here is I'm creating a data cube of our overview at 1 day temporal resolution. So that is a data cube which has 1000 by 1500 pixels in space and more than 2000 days. So where you have really observations at every day, if there are data, of course. So a lot of values will be just NA because you don't have any observations. And what I then do is I select any of the bands, just band 1, and then count over time how many non-NA values I have. And if I plot this, so that will, of course, do the processing now. And of course, this cube is also much bigger, but it's not taking that much longer. It will give me a nice plot where actually you can see where in the area you have a lot of observations and where you have, oh, wow. That was bad, wow. Not sure why this happened. Okay, let's run again. Okay, so I need to do some reloading here, I guess. So, okay, I have to reload the package and I'll do everything again. But I guess I have to reload the collection. So sorry for that. Probably need the overview. And I probably need the mask. So let's see how that works now. Probably I need to load the packages again, the color space and the gritter, right? All right, let's see how it works now. Okay, so no, that's wrong. I think that was a time series example. So this is a count reducer where I have a daily data cube. Let's see whether it works now.
So now you're doing counting BNAs and B01.
Yeah, so most likely if there is no value for band 1, there's also no value for band 2.
Okay.
So because so
do
either you don't have an image at one day,
Yeah.
or the cloud mask actually sets all the values of all the bands to an A. So probably it's most efficient to use a low resolution band here. Then it doesn't need to read the high resolution data, but I haven't done any tests on that. Good. Yeah, that's what I wanted to show you. So in there also you clearly see the structure of the Landsat images, so that you have these overlapping areas where you have a lot of observations, up to, I don't know, almost 50, but you also have some areas where you only have like 10 to 20 observations. So yeah, and in the same way we could also plot a time series. So in this case, I'm creating a monthly data cube. So the time resolution is 1 month. And again, I select band 1, but I'm now reducing over the spatial dimensions and again, count the values. So let's see how this looks like. That also addresses the question of seasonality in the data. So because of, yeah, calculating the median over 1 year is always biased in this case because I used a cloud coverage filter when I downloaded the images. So that means during the season where there's a lot of rain and clouds, I don't have any data. And this is what we will see in the time series, which should appear in a few moments. So yeah, so you see a time series with a number of non-NA pixels per month. And there you see that actually from October to May, you don't have almost any other observation at all. So this is of course due to the cloud coverage filter I applied when I requested the data from the USGS portal. Yeah, that's, I think, very helpful to get an understanding of an image collection and to take this into account. Okay, so as I said, there are some more operations which I just want to show you as an example that you can really create more complex chains of operations in it. So there's a fill time function, which just fills in A values, and the window time function, which can be used either to apply a moving window kernel over time series or to apply a reducer function over moving windows. So in the example below, we just define a new color palette, scale, so which I call color trend. So that is a diverging color palette, meaning that yeah, you have one central value which is 0, and then make a difference whether the values are positive or negative in our example. And that's a very, very, very simple method to analyze a trend of the time series which I just showed now. And therefore I was using a palette green brown. So I want to visualize whether pixels tend to become greener or browner. So the NDVI gets higher or lower. Good. So what we do here is a pretty complex or a bit longer chain of operations. So we compute the NDVI as before. Then we say we simply want to fill the NA values with the last observation available. So LOCF means last observation carried forward. So that is adapted from the zoo package. So that is similar semantics. Then I'm applying window time operations, which takes kernel -1, 1, and the window 1, 0. So that means that from the current point in time, you go 1 point in time back. And then you multiply these two values with these scalars. So that means -1 times the observations 1 t minus 1 plus 1 times the observation now. So, and that's essentially only the difference of successive observation. So, and then in the end, we reduce time and compute the sum of the differences of the NDVI over time. And that's a very naive method to assess something like the trend of the NDVI over the time series. So let's run it. Yeah, but it's only the final sum. It's not like you get the steps in between. Only it's reducing. Yeah, exactly. Yeah. But it's like a cumulative sum, and then you only take the last value. Yeah. So yeah, it's a bit more of work for the computer, of course. But let's see. So yeah, I have to say that all these functions are actually really built into the library. So it's all C++ based. Can be good, but also is therefore hard to debug if you encounter any errors, because I'm using the RCPP package to interface C++ code, which is very useful and friendly for developers. But of course, sometimes it's not so easy to assess why certain things fail and so on. Good, and that's also one example where I think changing chunk sizes manually would probably improve the performance slightly, but I'm not too worried about that. Good, let's hope there will be something. Yeah. So there you have this green-brown color palette, and then you just see that there are quite a few areas where actually it was deforested. There are some peak values, but also some slightly moderate changes, which is maybe also during just due to the data have been collected at different days of the year. So, so this is not really a useful trend analysis, of course, but only just an example of what you can do with built-in functions of the package. Okay, so the next thing I want to discuss is that you can also apply R functions, so user-defined R functions on these data cubes directly. But you have to define or think about how you want to apply the R functions before. So there are only very few package functions that allow to provide R function as an argument. And these are currently apply pixel, reduce time, reduce space, and apply time. So reduce time and So these three actually apply pixel reduce time, reduce space are also available for built-in functions, but optionally you can just provide an R function for that, for example, to compute the NDVI with R functions, if that is useful. But more useful is often reduce time and apply time. So reduce time, you provide an R function and that gets a multi-band time series as a matrix as input. So a two-dimensional array essentially, and the rows represent the bands of one time series, and columns represent the different dates. And then the output of this function, you have to be a bit careful, must be a vector of band values, and this is the new bands of the data cube. So it reduces the time dimension, so the result always has only one value per time, in time, but it may have several spectral bands. So I'm showing an example for this. Probably in our studio. Right, so I compute the NDVI, so that's kind of boring now. But now I'm calling the reduced time function and provide an R function as the fun argument. And that gets one argument, X, and that is what I just said. It's a two-dimensional array. And within X, you can access band values of the input data cubes, which only has one band value, which is NDVI, and then assess the time series like this. So what we do here is we create a data frame with two columns. One is T, so that it just gets a time index. And the second column is the NDVI at this time from the time series we get as input. And what we then want to do is just fit a linear model, so fitting a regression line over the time series of the NDVI, and then extract the slope of this regression line. So also similar, simple trend analysis method. So we just compute the slope of the regression line as long as we have enough values. So we say like, oh, we only want to do that if we have more than 3 different values. And then we return the result. So let's try that out. So it's really now doing things in R within the data cube. And that opens up, of course, a lot of flexibility. So in principle, there's no limit what you can do there. So you can use any packages that are available or use your own functions, everything. However, you have to be careful a bit because this function is executed actually in a new R process. The result is because everything else is in C++, so and there's no way to call like multiple threads in R from C++, and so that's a bit ugly, but it's executed in a new R process, and that means in this function you provide here, you cannot access values you defined before. So that doesn't access your current working directory or your current workspace. So that also means that you have to load packages you use in that function again. So that's very important to know. And also it is important that the function always returns the same number of values because the data cube model essentially says that for all pixels, you have the same number of bands. So then it would get confused if you have less values for one time series and more values for the other in that example. So therefore, it's always a good idea to think about NA values because quite frequent you end up with time series that are completely NA. So for instance, if you, I don't know, if modus data over the C or so, then you get complete NA time series, and then you realize that, oh, this is a special case, and that makes brings it to or produces an error. So yeah, and because this is also executed in a new process, it's also a bit harder to debug. So if you find errors there, so you get messages back from the R things, but yeah, sometimes it's just not so easy as you would do in R natively. So why is this useful anyway? Because as I said, so gdalcubes does everything chunk-wise, so it doesn't read everything into main memory, and that's, I think, some of the differences to other packages, and I think also to the stars package. When you do the processing in stars, at some point it will try to read everything into main memory. That may work for smaller data cubes, but at some point it might fail. So yeah. Okay, let's look at this. So this is the trend, simple linear model fit, and then the slope of the NDVI. And actually it looks, yeah, a bit more interesting, but still it's, yeah, nothing like a proper trend analysis. Okay, so let's what I mentioned so far. I have one more example, which is an example you often hear about when you start learning Google Earth Engine. So they come up with these greenest pixel RGB composite. So what you do is you compute the NDVI and then return the RGB values of the time where the NDVI has a maximum value. So for each pixel time series, and that's what I do in this time series. So I'm computing the NDVI again, only for 1 year now, just as an example for 2016. Our datacube has now 16 days of temporal resolution, so which is what the revisit time of Landsat 8 is. So because I want to, in the end, I want to return RGB values and not the NDVI value, I need band 2, 3, 4, and 5. So band 5 to compute the NDVI and the NDVI, and the others to return in the end. So I compute the NDVI and say I want to keep the original bands, and then apply an R function here. So I call reduce time again, provide a user-defined function as an argument. And what I do here is just use which.max. So that is just computing the time index where the NDVI value has a maximum value. And then I'm returning the RGB values, band 4, band 3, band 2 at this time index. And that is automatically executed over all time series. And then we can plot it, and for each pixel, it's actually then the most greenest value in this year. So let's see how that looks like. Yeah, so this is one example to create something like nice looking green composite images. Yeah. Okay, so that's about processing data cubes with the package. I have a few comments on how you can extract values from data cubes, which is important if you want to apply machine learning stuff. So to generate training data, for instance. So you have somehow created polygons or points with labels, and then you want to extract at those positions values from a data cube. So there are a couple of functions you could do for that. So one is query points. So you just provide vectors of x, y, and t coordinates, and then it extracts the point of the values of the bands at these coordinates. There's also a function query time series where you just need to specify x and y, and then you get the time series of all the bands of the data cube as output. So that can be used for time series classification or similar stuff. And then there's also a function called zonal statistics, which is a bit similar to what raster extract does for if you provide polygons as input. So it's computing summary statistics over polygons of a data cube. And because the data cube is multi-temporal in general, so it really gets you a vector data cube. So you have geometries and values, but you also have a time dimension and a band dimension. So, and I don't have an example here. I can maybe show one example I have, which is very minimal on the GitHub. README. So yeah, this is a very minimal. I'm actually using the same dataset there. Right, so I have a very minimal Landsat 8 dataset covering New York over 1 year, but only at very, very low resolution because, of course, CRAN doesn't allow you to come up with a package that has a gigabyte of memory. So what I do here is essentially I'm running this zonal statistics function, and that takes the data cube with an NDVI as an argument, and then it takes a geopackage file where it takes the geometries from. And this is, I think, some administrative regions of the New York area. And then what I do is compute over these polygons the median NDVI values and compute and return the object as a stars object. Then call the plot function, which is then the plot function from stars. Then you, for instance, get like something like a vector data cube with median NDVI values over time, over New York, over these features. So yeah, this is only a toy example here, but I've actually tried it out with more data. So and that, yeah, works out quite well. So I've tested this with around 500 gigabytes of Sentinel-2 data and 50,000 of polygons, which was like also administrative regions over Northern Westphalia in Germany, and also that depending on the resolution, of course, you use in the data cube. So on the 10-meter resolution, it took like 2 hours or so. And then you get the monthly time series of aggregated NEVI values over the polygons for 1 year. So that's actually quite useful, I think, to extract data and also to combine it with vector data, with other vector data, and generate maps in the end. Okay, so I have some internals here. So, but we can also leave the time, so there are 14 minutes left to for some questions. So, are there any questions so far? Yes.
Actually, there's some questions on Zoom.
There are questions on Zoom. Good. How can I read this? Good. Q&A? Chat. So there was an error with external graphics, which I actually have no clue. What I sometimes do when I get plot errors, I call def.off to reset the plotting device and try again. And then maybe the plotting region was just too small, so maybe you could just increase the size and try again. So, but I don't know any details. Then the question was why I don't need to provide a value for the argument n when calling the ndvi.call function. So that is passed automatically from the plot function in gdalcubes. So it automatically has a default number of classes or breakpoints it uses. So, and then it automatically passes this value to the function. So you don't need to specify this, but if you want, you can do it. But then you would also need the n breaks parameter in the plot function. So that means something like 10 breaks means that I think you would need to set 9 color values. Then there was a question, is the data independent of the cube? Yeah, yes. I mean, I don't really fully understand the question. I guess this is related to the differentiation between the data cube view and the data cube, which I understand is sometimes a bit confusing. So again, I would say that the cube is actually not independent from the data because it knows where the data comes from. So it's linked to an image collection, but yeah, the data cube view is not. Oh, there's an explanation. Cool. Like if the data set is monthly. Yeah, that's actually possible. So yeah, there are quite a few things you can do which do not make sense. So you can specify a data cube view with centimeter spatial resolution. Nobody will complain and the package will just try to do it. Although if you have like kilometer resolution in your data. So there's no reason not to do it for software. But of course it doesn't make sense. It will just use gdal warp and try to do it and then resample. And it will probably also work, but it will, well, consume a lot of processing power and a lot of time. So yeah. So yeah, that would work, but yeah, probably wouldn't make sense. Yeah.
So is it a bit like when you're working with netcdf files that you basically, so you can have, I don't know, hundreds of gigabyte NC file, and then you just first open it, and it's just a window into this file, and then you can extract the metadata, or you can work with the data without actually having to load everything into the workspace, i.e. you can actually work with 500 gigabytes or terabyte data as long as you have it on some storage device that just cycles through.
Yeah. So it does actually, but of course, I mean, I promise that I will work with the 200 gigabyte data set, which I did, but of course I didn't work on full resolution. So the whole story is I just used the data at 100 meters spatial resolution. And of course, if you do everything on 30-meter resolution, then it takes longer. Again, I think GDAL does a very good job and is quite efficient. So, yeah. But then of course you probably would use the plot function a lot if you work on high resolution, and then rather prefer a write net CDF, and then you get a large net CDF file, which then you can process further.
Plot the star subject and measure.
Yeah, this has this,
Lazy evaluation,
right,
basically.
right. Yeah, that would be a good idea.
Faster.
Yeah.
Okay, that's good. Yeah.
There was another question.
Could you say a few words about really beginning of the process and say how are you getting the images? Do you use some package, or are you downloading them by hand, one by one, or something like that?
One package I find very useful is a get spatial data package, which is not on CRAN but on GitHub. So in there you can connect to the Landsat USGS portal and also the ESA Copernicus portal and automatically download data from within R. That being said, that's often a nightmare because, for instance, the ESA Copernicus hub, if you want to order older scenes, then they have these kind of rolling archive, and so you're only allowed to download a certain amount of scenes per day or so. I don't know, I don't remember the details, but I remember that when I tried to set up the data for this tutorial, actually, I really promised myself, next time I do something like this, I'm gonna go to the cloud. So yeah, this is of course something which is annoying to download the data. And I clearly see that if the data is available on some cloud platform, it makes sense to go there.
And you personally, are you using this package?
Yes, yes. Danius, yes.
Two questions related to the data cube view and installation. For the data cube view, is there a way to handle the data if your data is in the paths? So if it's at the 1st, 11th, and 21st day of the month?
Can you repeat, please?
Yes, so if you have, say, PromoV data, PromoV is a satellite that allows you to get data that is on the 1st day of the month, 10th day of the month, 21st day of the month, and then for the next month, again, on the 1st day and so on. So can the package handle data like this?
Yes, sure. I mean, you just need to extract the day, the date of the image, and then it's fine. Yeah.
Then how do you use the data cube for that, where you need to specify?
Well, in that case, well, the data cube view is just how you want to analyze the data, right? So, but it would take care automatically that you aggregate the correct images. So, if you have like a monthly data cube, then it would probably aggregate 3 observations per month.
What about if you don't want to? What if you don't want to aggregate and just use the data?
Yeah, that's one option, or something like, you could also use daily all the time. That's one of the internals, which is a bit, or I think quite interesting. So actually the data model in memory is dense. It's just C++ 4-dimensional arrays, but it's chunked, and there is a special case for empty chunks. So if a chunk has only NA values because there is no images, so it will not consume any memory, and it will also not do the processing for these images. So if you have a very high temporal resolution, you end up with a lot of chunks that are completely empty, and then it's not so bad to do anyway. So therefore, it was also not so much slower when I just specified the 1-day temporal resolution in the count example here. Yes.
What if I want my temporal resolution going from July to July and from 1st to January? Can I define that somehow?
You mean the aggregation?
Yes.
So no, probably not. So yeah, I mean, you could work around a bit. So you could do something like defining different data cube views, and then use something like daily temporal resolution, and then use the reducer function. And there you can clearly say that the starting date is, I don't know, July 1st, and the end date is September 2nd or whatever. And then the next, so that would be a way to have like irregular temporal subsets, right? So that have different length. So that's not in one cube, but you could do something like having it in several different cubes, and then work around a bit. I don't know whether this would work for your use case, but maybe it would. There was another question, yes?
How would you compare the cube to the stars? Or what are each set of cubes best at?
With the stars package, the comparison?
In comparison.
I would say that if you have like Landsat, Sentinel data, Modus data, or anything where you need to reproject, warp, or you have overlapping images or irregular time, this is a lot of work in the stars package. But on the other hand, if you have regular data, like often you have in climate data or also global data, which are already kind of a cube or with regular time intervals and so on. So you could immediately reduce the stars package as well. So it's perfectly fine. So, and of course the stars package is much more flexible. So if you have higher dimensional data where something like atmosphere data where you have an elevation or pressure level, so that wouldn't work with gdalcubes. So it's really concentrated on this use case, satellite image collections, which are irregular, and then building something regular out of it. Another question? Yes.
You mentioned at the very beginning this issue that Munster is on 2 UTM zones.
Yes.
What happens if you try to load a collection where you have imagery from different UTM zones?
Oh, it's no problem at all. So it just, I mean, it's calling GDAL warp anyway, and there you have the target projection of your data cube. So just applying GDAL warp separately, and it knows that the input projection is different.
Can you specify a projection, or do you always need to?
You need to. Yeah. Are there other questions? Let's check Zoom. Does gdalcubes can understand the time dimension in netcdf files? All right, so this is nothing that works out of the box. No, I'm using gdal currently only to read images, and gdal, well, sometimes it has it in the metadata, the time information, but I think as far as I know, it's not like standardized how it is. Although of course in netcdf you have CF conventions and pretty standard ways to do it, but no, that would not work automatically. No. But yeah, there is a bit of a workaround which is under development, where we tried to bring climate model output into gdalcubes, and there you have actually time as one dimension in netcdf files, and there we are trying to make this possible in the collection format to define this, but that's under development. So, but in the latest version, it's not so easy. No. Good. Otherwise, thank you for now. Let's maybe have lunch now, and then, yeah, hopefully meet you later. So thank you.